Today I will talk about recent advances in HPO, which is a little bit an evasive title. I will talk about some of the recent advances in HPO, and mostly focusing on what the community calls multi-fidelity hyperparameter optimization. So a brief few words about myself. I am a professor of machine learning at the newly established University of Technology in Nuremberg, and my research foci are primarily on hyperparameter optimization, but also deep learning for tabular data, as well as reinforcement learning and multi-objective optimization. Today, my talk is going to go through some basics on black box hyperparameter optimization. That's a brief material which was covered in more depth today in Professor Bischel's talk in the morning. And I'll mention some recent Bayesian optimization tricks. The second block would focus on transfer learning for hyperparameter optimization and different modalities of transferring the performance predictors or the surrogate, as well as transferring the policy. And then we would move to dynamic hyperparameter optimization or hyperparameter optimization with fidelities. And we will cover some background on dynamic hyperparameter optimization and recent methods on dynamic hyperparameter optimization. So let's start with some brief background. The task of hyperparameter optimization is, as most of you are familiar with, a very crucial problem and still an open problem for the machine learning community. So what we are interested to do is we want to find the optimal design choices for typically deep learning pipelines in the sense of the optimal architecture, the optimal optimization related settings such as the choice of the optimizer, the choice of the learning rate scheduler, the choice of what regularization technique to apply and what should be the strength of the regularization. And the entirety of those design choices define the space of the search space of our hyperparameters. From a more optimization perspective, HPO as a problem is a bi-level optimization, where in the upper level we search for the optimal hyperparameters lambda star in the space of our in the search space of our hyperparameters. So we search for the optimal settings of a deep learning pipeline, such that if we train a neural network with those settings, in other words, if we train our parameters theta, the weights of a neural network with those settings, then the converged parameters of our neural network on the training set under the regime of those settings, this model, when applied to a new subset of the data, aka our validation set, then the performance would be as good as possible. So it is bi-level because the low-level objective, the optimal weights depend on what hyperparameters you choose. So depending on if you choose different learning rates, then of course the weights of the neural network are going to converge to different local optima, and as a result, the parameters depend on the hyperparameters. So how to run this optimization? This looks like basic, or to a certain degree at the first sight, basic optimization. Can't we plug it into a numerical optimization and solve it? Well, actually that is not so trivial. And what makes it non-trivial are the characteristics of this function here. The validation loss with respect to hyperparameters is a very complex function. It is complex for three reasons. First, it is very expensive. If you want to know what is the validation loss of a specific learning rate, first you have to train the neural network's weights with that learning rate until convergence on the training set, take those weights, and then measure the validation loss. So evaluating the loss of a particular hyperparameter, the validation loss is expensive. The second, the loss is non-convex. So we don't have yet a machinery of numerical optimizers to optimize non-convex functions. But what makes it perhaps more difficult than the first 2 points is that those functions are typically non-analytic. that you cannot take a derivative of your loss function with respect to your hyperparameters. I say typically because for certain subsets of hyperparameters, you can actually compute the gradient of the validation loss, for example, with respect to learning rate. But the necessity for such type of approaches is that in the update rule of your parameters, think an update rule like a gradient descent update rule, then the hyperparameter must occur as a variable in this update rule, such as the learning rate. If the hyperparameter doesn't occur as a variable in the update step of your optimization procedure, then you cannot backpropagate through it. And this includes all promising, or let's say, almost all interesting hyperparameters, such as the choice of which optimizer to use, whether it is ADAM or RMS prop, whether you need a convolutional neural network or a transform architecture. Those choices do not occur as variables in your update step of your optimization algorithm. So gradient-based approaches do not apply for a wide range of hyperparameters. So we have a function that is very expensive to evaluate, that is non-convex, and whose gradient or derivative we cannot compute. And what we want to do is still we want to minimize it. So what is our approach to it? Well, basically this becomes a black box minimization or black box maximization approach. So we want to find the optimal configuration that basically results in the minimum, a minimum or the minimum of this function. And in order to do that, the most simple approach is a black box search. A black box iterative search. So an iterative search is a common mechanism in numerical optimization. Gradient descent is an iterative search, but also Bayesian optimization, as you saw today, is in fact an iterative search. And what we do there is we start with some initial hyperparameter values and we measure their performances. In the context of HPO and Bayesian optimization, we refer to those initial evaluations as the initial design. And then in a sequence of steps, we have a magic function here that recommends what should be the next hyperparameter to evaluate. These magic functions are all what we are looking for. Those are the search algorithms. And most of this talk today will focus on those magic functions. After our magic function suggested the next hyperparameter to evaluate, then we would evaluate it, meaning we train a neural network with those settings, take the converged weights, measure the validation loss for that particular hyperparameter configuration, add it to the history, and continue until we run out of budget. In the end of the day, what we report is the hyperparameter that achieved the smallest, for instance, validation error or the highest accuracy. If it is accuracy, it's a maximization. If it is error or loss, it is a minimization problem. And the $1 million question is, what is this point here? What is this algorithm that, given some evaluations, recommends where should I look next? There are two different approaches at a very high level. Either we train this policy directly, or we use an approach that is known as Bayesian optimization to decompose this policy into a surrogate acquisition mechanism. In that regard, Bayesian optimization is also a black box HPO policy that, given a set of observations about the performance of hyperparameters, basically recommends what configuration to evaluate next. So that's all it does. Given a set of evaluations, recommend where to search next. But it does that by means of two components. First, a performance predictor. The performance predictor is basically a probabilistic regression model that tries to mimic or approximate the black box function that we don't know in order to fit to the points that we have observed so far. So if you have this black box function here, then we have observed those 3 points, and you see that this green line is our performance predictor that passes through the points that we have observed. And it is probabilistic in the sense that it computes a posterior distribution of the response, in other words, of the validation error or validation accuracy with respect to the hyperparameter and the x-axis. And then the acquisition looks into this performance predictor and judges in which region it is more likely that we have a good good configuration in the sense that in which region are we expected to have a configuration that has the highest possible, in this sense, in this illustration validation accuracy. And an important trick here is to search for regions that we did not explore yet. And in order to do that, we take into account the uncertainty estimation of the posterior variance and probe regions that both have a high posterior mean, but also high posterior variance. A typical acquisition function, there are many different acquisition functions, as you know from the talk today, is the expected improvement. And that basically measures if you take the posterior distribution, for example, at this point here, this lambda, you would notice that you have here a density function. Assume that this is a Gaussian density function. And what we are looking for is if we take the line that passes through the best observed response so far, in other words, the point with the highest observed y-axis, and we take a line through that, we want to look into what area of the density function lies above that point. In other words, if our estimated performance is, in this case, for a minimization problem, we are looking to be below the best. For maximization problems, we look to be above the best. And we check what area of our posterior density function of the response with respect to the configuration is above the line for maximization or below the lines. In other words, by how much do we expect this configuration to improve the best performance we have seen? The higher, the better, and that is what this function A evaluates. So basically you see here that this is a promising region because it has a high uncertainty and it has a chance of being better than those observed points because you have a Gaussian distribution here and there is some area that is above the best observed point. Now, that is the common Bayesian optimization procedure, and that is an old approach, but still it works well for hyperparameter optimization, and it is a hard-to-beat baseline. Well, it is a hard-to-beat baseline only if you marry classical hyperparameter optimization with a series of tricks. And those tricks could be summarized in essence as belonging to three main families. You have to transform the input, and those tricks recently were popularized by a method known as HPO. So the first is the input transformation for non-stationarity. So you apply typically an input warping known as Kumara-Swamy. I will not go to the details, but those are one-liners in sklearn. So it's very, very simple tricks to implement, and they make a difference in practice. The second is the response. In other words, those points here that you see, the y-axis, we use Cox transformation in order to make them more Gaussian-like, the distribution. And the third is, instead of using a single acquisition function, we use a multi-objective optimization. We combine more than one acquisition functions. So if you transform the input to remove to make it more stationary, if you transform the target to make it more Gaussian, and if you use more than one acquisition functions, then Bayesian optimization can achieve state-of-the-art results, as HPO demonstrated. And actually, taking some results from the original HPO paper, we see that each of those elements actually play an incremental contribution. So you see, compared to the basic BO, if you add a robust acquisition that uses more than one acquisition functions, instead of maximizing one of them, you maximize, for example, a linear sum of three of them or four of them. So you use more than one acquisition. That gives a lift. And then if you remove non-stationarity, then you have another lift. And if you remove, for example, heteroskedasticity, then yes.
Is this additive or just checks separately non-stationarity, robustness acquisition function? These improvements are additive or increment?
For example, you have to check this HPO without heteroskedasticity versus HPO in order to evaluate the effect of this component.
A focus on sub-second at 0 bucks. Yeah, this is with the robust position. And for example, and then let's see with no speciality. Are they adding up or they are independent?
Not adding up, yes. Yeah, it's incremental, yes. And in terms of making the good old Bayesian optimization state of the art, there are even more tricks, such as the tricks that you see in a coming presentation that is in 2 days, if I'm not mistaken, by the guys of Google Vizier. So I will not stay a lot in describing this library and the approaches behind it. But basically, one could summarize that it is about defining your search space well, or normalizing your hyperparameter variables, on warping the response or the observed validation error, and then on modeling the posterior distribution, as well as using more interesting optimization techniques to find the maximum of an acquisition, especially in continuous search spaces, because as you know, the acquisition is also a non-convex function. So you'd see more about the details of the Google Vizier, but just as a brief, it is similar to HPO, but you have also this aspect of an evolutionary search strategy to maximize the acquisition function. Great. Recently, there is also another direction of doing HPO, and that is the so-called likelihood-free Bayesian optimization. Likelihood-free BO is very interesting and to a certain degree brought some novelty to the community, because it advocates for actually performance predictors that are non-probabilistic. And if you do not need a probabilistic performance predictor that doesn't produce necessarily a posterior distribution, then you can use standard neural networks. And that is nice because we have libraries for optimizing neural networks. People know that they are flexible enough, they have low bias. And the intuition how could one actually use non-probabilistic performance predictors for doing HPO is to convert the procedure of Bayesian optimization with expected improvement to weighted classification. In the original paper, they have a proof that those, in the end, optimize exactly the same thing. So it is proven to be equivalent. And what we do here is we set a threshold. The threshold is this line. So we want to maximize this function. We want to find a region where the performance, the accuracy is the highest possible with respect to the x-axis. And what we model is how far away are we from this threshold. So if you are far away from the threshold, then your probability of being away from the threshold is 1. And if you are below the threshold, the probability of being below the threshold is 0. So you can model the fact of how far away you are from this threshold as a binary classifier. With a small trick, and the small trick is that we weight the positive instances, in other words, those that are above the classifier, by how much above the classifier. Sorry, those that are above the threshold, we weight by how much they are above the threshold. So we don't want to give the same weight to this point and that point if this point is further away from this threshold than the other one. So it turns out that a weighted classification that has a weight of how much better you are than the threshold multiplied by a normalizing fraction to normalize the two terms, and that is the number of positive points divided by the total points, that this very simple. So if you take this term away, and if you take this term away, this is just logistic loss, right? It's the simplest classifier that we can have in machine learning. And with just two small modifications, you add a term here weighting by how much you are above a threshold, and you have just this fraction here as a constant. With those two small additions and having a very simple function, you can get the weights of a classifier, and instead of them using the standard BO step with surrogates and acquisitions, you can simply select the configuration which has the highest estimated probability of being above the threshold. And that is a very cool thing. Yeah, there are early experiments that show that this can be promising, but promising from an empirical perspective. But what I think this to be cool is because this brings HPO back to simple classification that everyone can implement in 10 minutes or so. And the authors present that actually the performance of this likelihood-free, non-probabilistic classifiers for doing HPO is as good as Bayesian optimization with expected improvement or probability of improvement and using probabilistic performance predictors such as Gaussian processes. Please.
Okay to ask you?
Of course, it is okay.
Have you played around with this yourself or looked a bit more? I mean, I would be really interested in some more details regarding cofactor performance, and I looked into this a couple of times and found it also very interesting. We have further experience with this?
Yes, we implemented it, we tried it, we couldn't reproduce these results. It's not in our experiments as...
You could not?
We could not. But it's not also that bad. Yeah, so it's similar-ish to a yeah, but not much better than a classical BO.
Okay. Did you, I mean, use, sorry if I can ask a second question.
Sure.
I mean, treating this as a classification problem, I mean, enables an even larger zoo of surrogate models. Did you exchange both and to play around with that?
We tried MLPs for the simple setting, but you are perfectly right. One could add transformers, in-context surrogates. One could add meta features. So that is, I think, the biggest strength, exactly what you mentioned, that then you can use basically, you can plug transformers as a classifier and do all the cool stuff you can do with neural networks. Yeah, that is a nice point. Thanks, Bernd. And feel free to interrupt at any point. That's valid for everyone. So the next and major thing is transfer learning. So starting HPO from scratch is not what brings, let's say, is not very promising as a direction, because if you start about a function, then you know nothing, then you need a lot of evaluations to find the minimum. So a way to improve this performance is to transfer learn the surrogate. And a simple illustration of transfer learning the surrogate is, consider you have the performance of a certain neural network hyperparameterized with lambda on 3 different data sets. And we see that this hyperparameter has some performance curves that look very similar. So if you change the data set, of course, the actual accuracy changes a little bit, but the behavior of the hyperparameter in terms of the pattern is similar. And if we now have a new data set, and I start with evaluating this first hyperparameter here, if I would not transfer the knowledge about how would the performance function look like as a function of the hyperparameter, then the best guess I can do is this flat line. But if I just transfer the average or the expected performance curve given this point here, then this would be the red line. So I already start with knowledge about what are typical performances of that specific algorithm with respect to those hyperparameters across other data sets. And that is an information I can transfer to do HPO efficiently on a new problem. And the effect there is what we want. We want fewer HPO trials to go to the minimum, as it is shown here, where if we meta-learn a performance predictor on lots of sine waves, then we would see that if we start with one observation, after having meta-learned this performance predictor on general sine waves, then it already knows that in these regions where you have no observations, that the estimated performance is similar to a sine wave because you transfer this knowledge. And after doing a BO step and evaluating the next configuration, then the estimated performance on the regions that you're not explored starts to look like a sine wave because the model has been trained from similar problems before. So we see that we need much less evaluations to reach to an optimum. Please.
You said that you, well, Pulpensis use the average model basis. Had many DSSs are likely that are identical or have a very similar tendency. So is there a smarter approach to differentiate this show data set is constituted the best place is that.
Yes, so I think that's a very good point. There are two approaches to contextualize the performance predictors on the characteristics of the data set. The first approach is to represent the characteristics of data sets as in a vector representation. We call those meta features of a data set. And the second approach, which recently is very promising, is to use in-context performance predictors, such as those that some of you know, PFN networks. So those are models that take the full data set, and implicitly in the neural network you extract information about the problem by the attention across the data points. So those two approaches are the ones that I would know, and they play a role. Yeah. So no one does it naively anymore. Cool. So the first approach is we can take a surrogate, meta-learn it across different problems, and fine-tune it on a new target task. That is what this FSBO method does. So we have a set of evaluations across a number of data sets. We call this a metadata set because this is a data set of evaluations about the performance of hyperparameters. And we want to learn a performance predictor that is probabilistic and feed it across the evaluations of a metadata set. So a very simple meta-learning setup. You want to estimate the performance of configurations across different data sets. And you have an expectation across all the data sets and all the observations in your metadata set. And then on a new task, we initialize the Bayesian optimization, not with a random surrogate, but a surrogate that was meta-learned from previous performance functions on other data sets. And other researchers moved this one step ahead, and especially the work by Samuel Müller and the other colleagues actually does meta-learning of the performance predictors, but uses in-context surrogates instead of surrogates that are fine-tuned on a target task. And this in-context meta-learning enables you to avoid doing adaptation on the target task because you capture the characteristics of the target task by providing the full context of the evaluation so far on that problem. In fact, this is an application or an instance of in-context probabilistic models, more generally known as more general probabilistic models that are in context, which are known as PFNs. And the idea here is that assume I want to predict the target of a test instance. So I have x4 and I want to estimate y4. And I have another test instance, x5, and I want to estimate y5. And I have 3 training examples. So what I do here is, instead of having a function that just takes x and estimates y, as you do in classical supervised learning, now I feed the full training set as an input to my model. And we call this the context. So it is an in-context model because it doesn't just take the features for whose target we're interested in estimating, but also the full data set as an input to the model. And you would say, well, you would still need to learn it for the data set, that's true. But the trick here is that we pre-train it across millions of data sets, and in a way that those large sets of data sets are diverse and rich in a sense that they could then extrapolate out of distribution to a new data set that you have not seen before. And the other nice point here is that the authors show that you can actually use synthetically generated data sets, millions of them, and meta-learn this in-context probabilistic model in order to then deploy it on real data set. So it is meta-learned, it is in context. In addition, it is meta-learned from synthetic data sets. And that can be also transferred to hyperparameter optimization, because if you check the essence of hyperparameter optimization, it is a regression task. You regress the performance of configurations. So one can use those pre-trained or meta-learned performance predictors also for Bayesian optimization, with the difference in contrast to classical Bayesian optimization with Gaussian process, you don't need to feed a Gaussian process anymore. You use the meta-learned transformer network, those are large transformer networks, and feed the full set of observations so far, this data set D, as an input to the transformer, and then you feed the hyperparameter that you are interested, and you estimate the performance of that model. And how would it work on a new data set? Remember, it works because it has seen dozens of millions of other problems in the past. So it is meta-learned on lots of synthetic data. And those synthetic data are so diverse that eventually your real problem would look like some of those synthetic problems. So there is a transferability that actually is successful. And such in-context surrogates have been shown to actually perform as good as classical Bayesian optimization with surrogates that are learned specifically for that target problem, at the benefit of not having to adapt your surrogate on the new task. There is also another direction, always in terms of meta-learning performance predictors. So far we saw the classical case, you meta-learn and you fine-tune. That was FSPO. The second case, you meta-learn but do not fine-tune because you use context. There is also a third approach, you meta-learn and you fine-tune, but not for a regression task. Instead, you can look at hyperparameter optimization as a learning to rank task. And the intuition here is the following. Consider that you have those two cases. So you have a black box function shown in red, and you have 3 evaluations on this black box function, and I have fitted 2 performance predictors in black, one on the left and one on the right. And the one on the left actually fits more tightly to the observed data points. The one on the right doesn't fit so well to those data points that you have observed. Yet, would you select this as your surrogate, as your performance predictor, or would you select the right-hand side? You'd select this one because in hyperparameter optimization, what we care about is that the minimum of the surrogate is the same with the minimum of the black box function. In fact, we don't even care that they are close. We just care that the minima match. And as a result, one way to ensure that the minima match is that if you take pairs of configurations, their performances are such that the rank is preserved. For example, that the estimated performance of this point is below that other point, both in the black box function and also in your approximated function. And that way, you approximate the location where the minima exist instead of just fitting a regression line, which might not fit well to the minima. For example, here you see that the minimum of the approximation is here instead of here where it should lie. And that brings to the question, actually, that hyperparameter optimization is not a regression task. That's what is, let's say, the main way to approach it, but that's probably incorrect. What we need are performance predictors that preserve the rank of the top configurations. Yes, please.
I guess I would intuitively agree, and I mean, I guess my question is, why are you not doing anything then like that? I mean, this has also not much to do with meta-learning as you state. I mean, this is a fundamental core question about how to do DO. And I mean, I guess you also know, I mean, if you look at what they're doing in surrogate-assisted evolutionary algorithms, in a certain sense, that is somewhat old news. They have done this, they have shown this works. Why is another us and now bring this?
I could speculate about the reasons, and I would speculate that the learning to rank family of approaches are perhaps not very popular. The second approach is that it is not trivial to do a learning to rank that is probabilistic, to learn probabilistic ranks, or at least I'm not fully clear in my mind how would one do it in a probabilistic manner. The authors of this work do it with a deep ensemble approach, so they basically create an ensemble of k rank estimators and then create a posterior distribution from the ensemble, but there is no, let's say, clear principal uncertainty estimation as in the case of Gaussian processes. That would be my speculation. But Other than that, I like this approach personally, if you ask me. So, as we said, in hyperparameter optimization, only the best configuration matter. So what you need is a performance predictor that correctly predicts the performances of top configurations. I don't care that much to predict the performances of bad configurations. I don't care about learning curves learning rates that diverge. I care about those learning rates that converge well. Which one among those that converge well is the best? So I need to model well regions of my search space where top configurations lie. That is similar, for example, with search engine optimization, where given a query, let's think of the query as lambda, you are presented a list of results. Let those results have a relevance, how relevant they are to a query in a search engine, and that is our loss function that we want to optimize. Typically, what we care about is how relevant are the first page of Google results. No one checks anymore the 100th page of Google results, right? So it's not really a regression on matching the relevance, it's really getting the top results that are really reliable because that's what people click. And that is a similar story here. We want to correctly estimate the performance of top results, and that becomes a learning to rank approach. There is a machinery of loss functions for learning to rank. One of the starting approaches is a listwise learning to rank loss, where you try to estimate a relevance such that for those configurations whose true rank is the highest possible, then your relevance would also be high. And that is ensured because you normalize them by the contribution of the relevances from the other configurations. So that ensures that you keep the rank. And in addition, we have here a weighting factor that puts a higher penalty on items that are high above in the rank. So think of it like a weighted loss term, where you have a weight that is proportional to the position in the rank, and then you have a term that pushes estimated ranks to be high for configurations that are relevant. And the authors suggest that if you create such rank estimators and also use them with an ensemble approach to create the posterior distribution, that this is comparable to the other approaches that use Gaussian processes. So empirically speaking, this doesn't look like a bad idea if one figures out the way how to construct uncertainties, perhaps a little bit better than deep ensembles. Then there is the other approach. Forget Bayesian optimization. Let's directly build the policy. What that means is I give you a history of evaluations and a new configuration, and we want a function that directly tells what is the next configuration to try. Instead of having to build a function that approximates the performances and then an acquisition on top, let's merge both of them into a single function that directly tells you what is the next configuration. The first approach to doing that, to meta-learn the policy, is to pose the problem as a reinforcement learning problem, in the sense that the state is the history, the time step where you are, the remaining budget that you have in terms of your HPO budget. The actions are which hyperparameter you choose, and the reward is, well, across the series of hyperparameters that you evaluated, what is the one with the highest validation accuracy. So you want to have a way of posing the question of HPO as a reinforcement learning, and the reward is just the best achieved accuracy or the smallest achieved error so far. And then what we do is we meta-learn an HPO policy to maximize the discounted cumulative reward across tasks. So in essence, it is a standard meta reinforcement learning approach with a twist that I'm not going to go into details. The policy model is what they call a neural acquisition process, is some form of a transformer. But it is meta-learned in a meta reinforcement learning step. And this approach then is a transfer learning of policies directly. So this detaches itself from the Bayesian optimization family of methods. And the results, empirically speaking, for this approach show to be competitive. And so far, the HPO community played a little bit with reinforcement learning as HPO solvers, but it was not successful until this paper. This paper showed that actually RL-based approaches for HPO can be state-of-the-art if you meta-learn the policy. The other type of policy transfer is actually the transformer policy of OptFormer. OptFormer is a very generalistic language model where you provide the history of evaluation so far as a free text. So you just construct the evaluations as a prompt, and then you ask a question: what is the performance of this configuration, given that I have tried those configurations so far? So pretty much at inference time, it is next token prediction, as you do with language models. So that is bringing language models as both as policies for HPO. So replacing the surrogate acquisition now with a language model. And in fact, this approach, as language models have shown in many other domains, also works very good for hyperparameter optimization. So what the authors did is that they learned from data created by other optimization policies. For example, optimization policies, let's say you take a sequence of evaluations from a Bayesian optimization procedure. And then they meta-learn a policy that clones the behavior of those optimizers and predict the hyperparameter response of a particular hyperparameter. So it's more this question answering language modeling. Now the question is, given those hyperparameters, these problem characteristics, and those performances in a free text, what is the performance of a configuration, also raised as a question in free text. And surprisingly, this works very great. Yeah, so OptFormer is currently believed to be the state-of-the-art in hyperparameter optimization. Unfortunately, it is evaluated on Google's internal data. We cannot reproduce it. However, even on some of the benchmarks which are public, still it is a very promising approach, although there is a contamination in these results because of transfer from internal data and then evaluating it on public benchmarks. So this is not meta-learned exclusively on the benchmark itself. It's evaluated there. I saw, Matthias, you had a question or comment? Good. So then we move to the other step. We have about 10-15 minutes, and that is the dynamic HPO procedure. So we talked a lot about black box search. Deep learning is not really black box. No one does it as a black box search. If you try to implement some new method, you look a little bit into your training loss and the validation loss, and if you see crazy things like the training loss goes down or it is not converging anymore, you stop this run, right? You wouldn't let it run until the end. That is an instance of what we call gray box evaluation or multi-fidelity evaluation. And that means you evaluate the performance of a configuration at a budget. Budget being a subset of your training data. You can decide to run an experiment quickly or maybe 5% of the data. You could let it run for fewer epochs, or you could use, in case of ensemble building, less ensemble models. And we see that there is some decent rank correlation. So those configurations that are well performing in the early epochs, they are also performing well in the last epochs. So the first intuition is, well, let's just keep the ones that are on top, those that are performing well already in the beginning. That is the intuition behind a method known as hyperband. So what we do is a process known as successive halving, where we have some decision points, for example, after 10 epochs, after 30 epochs, etc. And here we check the performance curves, those learning curves, and we keep just the good performing configurations and discard the others. And then let them run for a little bit longer until the next decision point, then ignore some of the configuration and keep only the good ones. And at each decision point, we just take the top ones and continue training them. Hyperband does also something more on top of this. It has different sets of decision points, because you don't know, should you evaluate configurations after 5 epochs, after 2, after 7? It depends whether configurations have converged or not. So you have different sets of decision points known as brackets, But those approaches also have a problem. And the problem is, could you guess a case where a certain hyperparameter configuration, certain settings, in the early epochs have bad performance, but then at the end of the optimization have good performance? What kind of neural network regularization approaches would result in such a behavior when you have strong or weak regularization? So think about it. If you have weak regularization, does your model converge quickly or slowly? Assume you set regularization to 0, drop out to 0, or weight decay to 0. Will you converge more quickly or less quickly? Depending on the assumption that you have a decent learning rate. Yeah? So intuitionally, you converge faster. Yeah? The less you regularize the model, the more quickly you converge. But that is an issue. You converge quickly, and then Hyperband would think this is a good configuration simply because it is not well regularized. And that, in the end, will end up to be not such a great configuration. So some well-regularized models, they need time to converge. Killing them early is not optimal. I will skip the motivation for the sake of time, but we can actually use a more dynamic way of doing HPO, but in order to present that, we have to first consider the aspect of expected improvement for learning curves. And what we have here is consider two curves, the blue and the red, and both configurations have been run until a particular number of epochs. So the red is run for a few more epochs than the blue curve. And now you want to guess or predict the performance of the blue curve at some future optimization point. For example, after 100 epochs or until the end of your optimization budget in wall clock time. And your prediction is measuring the posterior distribution. So you have a density function of your performance given your configuration, and assume that this is Gaussian. An expected improvement for learning curves, what that will do is it will take the best observed validation accuracy on any learning curve so far. That is the global best performance you have seen on any learning curve. And we'll check what area of your posterior distribution, in other words, of the posterior density function, lies above the best observed point in any learning curve. The higher this area here, the most promising this configuration is with respect to your prediction. And at the end of the day, we would then select the learning curve to be most promising if it has the highest possible estimated improvement on top of the best observed so far. So that is a mechanism for judging whether a curve is promising or not based on a prediction of its performance. And that brings to a generalized dynamic hyperparameter optimization procedure with learning curves. You would feed a surrogate, which in this case is a time series forecasting, as we've shown, a probabilistic time series forecasting, to predict the learning curve's performance at the next budgets. Then our acquisition is the expected improvement for learning curves that we just mentioned. We could also normalize it by the cost of the model in order to avoid spending too much time on very expensive models. And instead you might want, if two models are equally promising, then you might want to favor the model that is less costly. For example, if you have a 100 billion model and a model with just 1 million parameters, if they show to have the same expected improvement, you might want to favor the smaller model. So the cost aspect there is a typical element in Bayesian optimization. And there is a point here. The point is, where do you want to look whether this curve will have a promising progression in terms of your prediction? Do you want to look it into the next epoch? Do you want to look at the end of the optimization? This is a choice, a hyperparameter of your search technique. There are different approaches. Some authors check the performance at the next epoch. Some check the performance at the final epoch. And then what we do is we advance that particular learning curve that was selected to have the highest expected improvement at that check of the acquisition for one more epoch. So we decide to give one more epoch to that configuration. And in those approaches, we never kill a configuration, we never discard it. We simply have a controller mechanism that decides which configuration to resume and continue to train for one more epoch. So it is dynamic in the sense that it uses learning curves and multi-fidelity optimizations, but configurations race. So they race in the sense that we have a controller mechanism to decide whether we advance this configuration or that configuration for one more epoch. And we might have thousands of configurations in parallel that are being evaluated. And that approach improves upon some of the deficiencies on hyperband in the sense that we can have a higher fraction of performance promotion. So this plot measures what fraction of configurations were in the bottom two-thirds of configurations at some previous budgets, but which our configuration decided to resume at some later step of the optimization because, for instance, other regions of the search space were not promising, and then our surrogate now has less uncertainty in those configurations that you evaluated, and suddenly regions that previously were uninteresting are interesting at this point. And additions of this approach is to meta-learn actually this performance predictor with costs, and it uses cost awareness and meta-learning. You have a hands-on session on the Quick Tune tool, but I've just mentioned that it is an instance of what we described with two differences. You meta-learn this time series forecasting for estimating the progression of a learning curve. Second, you estimate the cost awareness, so both this function and that function there in the acquisition are meta-learned. And you also use dataset meta features, as your colleague previously asked, whether we want to contextualize on the characteristics of the dataset. For instance, here in this approach that is known as Quick Tune, it is being used. And you'll see more about this. There is a hands-on session, so I'll skip the details. Then the other interesting approach to a certain degree is to use the scaling law nature of the curves to implant our domain knowledge about the characteristics of the problem, that learning curves typically look like an inverse logarithmic in the sense that the loss goes down and then somehow you have diminishing return, and those type of functions can be modeled as scaling laws. And in order to learn a performance predictor that uses scaling laws for a given hyperparameter configuration, then the authors of this work train a hypernetwork that generates those three coefficients of a simple scaling law function across budgets B. And that in that itself can be then a performance predictor that now has a strong assumption, a strong bias on how learning curves look like in order to implant our knowledge about typical shapes. And that works to a certain degree well. And in addition, experiments show that for large language models, actually there is a very strong scaling law property. That was not before this paper, so that was not news. But the fact that we can use this for HPO, it was shown that also this can be done efficiently. And those configurations that work well at small model sizes also work well at large model sizes. And if you use that scaling law performance predictor, you can find the best hyperparameter configuration if you would evaluate that on the full budget, even if you do HPO search on something like 25% of the budget. 25% here is just the model size, considering it as a form of budget. There is also the other interesting extension of in-context performance predictors to do dynamic HPO that is similar to what we saw before, where we had this PFN in-context performance predictors for the case of black box HPO, and now we can also transfer it to the case of learning curves. So we could also have transformers that take a set of learning curves observed so far as our context, as our data set of observation, and then given a new learning curve, estimate the performance at subsequent budgets. And that can be meta-learned on lots of synthetic learning curves. That is the work of also coming from Frank Ruther's team, a recent work on dynamic HPO with in-context performance predictors that shows state-of-the-art results. And for example, you see that it is better on some of those benchmarks compared to this scaling law approach we saw before, or the dynamic HPO approach that we saw. So these last three methods that I mentioned are those three lines here. And this shows the power of actually meta-learning the performance predictors. The previous two did not meta-learn the performance predictor. Great. So the conclusive remarks are due to, we have still 4 minutes for questions, but the conclusive remarks are: 1, Bayesian optimization with tricks is still a strong baseline. If you use Bayesian optimization, do not forget to transform your input. Do not forget to warp or transform the output to make the response more Gaussian-like. And do not forget to use a multi-objective acquisition function. The second point is dynamic hyperparameter optimization has the potential to scale HPO, because you can do HPO on small model sizes and use scaling laws to actually then transfer these optimal configurations on large model sizes. This is an interesting property for language models or for transformer-based foundation models. And the third is that actually language-based HPO policies are promising, such as OptFormer. So you can actually learn language models, fine-tune them on text-expressed performance history in order to conduct HPO. What is missing in this talk, which is also very important and recent, is parallel and asynchronous hyperparameter optimization. The very promising direction of mu transfer and maximal update parameterization. HPO and foundation models on both angles, HPO for foundation models and foundation models for HPO. You have both those aspects, but there is a very interesting talk tomorrow by Frank Ruther on AutoML and foundation models that I would recommend you attend. And I did not mention libraries and tools. With that being said, we still have time for a couple of questions, and I would be very happy to hear your questions, comments, any point of interest that you might have.